So we will continue our lecture where we were talking about one random variable, where we looked at the moments of one random variable in the probability distribution, moments of the probability distribution of one random variable, which was the mean, the variance, skewness and kurtosis. Now we extend our discussion to include two random variables, say x and z, and we talk about something called the joint distribution. So in order to understand the joint distribution, we will talk of a particular example. So suppose the two variables that we are talking of is So suppose the two variables that we are talking of is h height, which is h, and say weight, which is w. Okay. So one individual may have will have both of these variables, and suppose we collect the data on the different individuals in your class, and so we collect this is the number, serial number, and we have individual 1, individual 2, individual 3. For each of you we collect the data, and we have your name over here, and we have height and weight. So say the first person has a height of 5 feet 6 inches and a weight of 65 kgs. The second person has a height of 5 feet 3 inches and a weight of 58 kgs. The third person has a weight of 5 feet 5 inches and a weight of 70 kgs, and so on and so forth. Okay, so as you can imagine, another person may have a weight of 5 feet 5 inches and 62 kgs. Another person may have a weight of 5 feet height of 5 feet 11 inches and 85 kgs, and so on and so forth. Now, how do you describe a joint distribution of these two variables? So in a single distribution, you just had one x-axis on which you plotted the different values of that particular variable. In this case, you have an x-axis, or you call it h over here, and here you have another axis which you call w, and you take all the values of h. In this particular case, your values may go from something like 5 feet to something like maybe 6 feet 6 inches, and you have 6 feet 5 feet 6 inches. We can even say 4 feet 6 inches and 5 feet. Okay, suppose this is the range of values of your height, and the range of values of your weight goes from say 40 kgs to something like say 100 kgs. Okay, so 40 kgs and 70 kgs and so on. Now think of it being a floor. So on the floor we make grids on the floor. So we make little tiles on the floor or little grids on the floor, and we call these individuals whose heights and weights have been tabulated in this table. So we call these individuals and we say, please choose that particular height that you belong to and that particular weight that you belong to. And so suppose if you are 5 feet 6 inches and 65 kgs, then you belong somewhere over here. You go and stand in this grid, this part of the grid. Another person 5 feet 3 inches and 58 kgs, so you belong somewhere over here. So you go and stand here, and you divide the individuals in this particular sample like this. So in this square, maybe there are 5 people standing here. In this square, maybe there are 10 people standing here. In this square, maybe there are 3 people standing here. In this square, maybe there are again 5 people standing here, something like that. So you divide up your entire sample and make them stand over here. Now suppose you could sort of imagine that you take these individuals and you make them stand on top of one another, if they could possibly stand on top of one another, then the surface that will be formed on top of this entire group, the surface that will be formed, this surface is basically the joint distribution of height and weight. So, can you visualize it now? It is like a hill on top of this two-dimensional axis, and the height of the hill will be highest where you have the most common values of both height and weight, and the bottom of the hill will be those places where it is less likely to find that combination of height and weight. So, you may find that it is uncommon to find very tall people with very small weight and very short people with very big weight. So, you may find that it's sort of this probability distribution really sort of you find very few people in these outliers. On the other hand, you may find that short people typically have higher weight and tall people usually have higher weight. Short people have less weight and tall people have high weight. So, this is basically, and what is on the y axis? It is the probability density of this joint probability distribution function. Understood? So, this is the probability density of the joint probability distribution function. So, if you now know what is the probability density, now we come and define another moment of this joint distribution, which is known as the covariance. So, remember that covariance can only be a moment for a joint distribution and not of a single distribution. What is covariance? Covariance is the expected value of x minus mu x multiplied by z minus mu z, and it is denoted as sigma xz. So, what is it? It is basically a measure of the linear association between x and z. That is, as x varies, how does z vary? As x goes up, does z also go up, and as x goes down, does z go down? Or is it that as x goes up, z goes down, and as x goes down, z goes up? Is there a positive covariance or is there a negative covariance, or is there no covariance at all? Okay. So, the units of this, because it is x minus mu x multiplied by z minus mu z, the units are units of x multiplied by units of z. Okay, so sometimes it makes no sense, but these are the units of covariance. So, covariance of x and z greater than 0 means that there is a positive relation between x and z. As x goes up, z also goes up. If it is less than 0, it means there is a negative relationship. That is, as x goes up, z goes down. And if they are independently distributed, then covariance of x and z is equal to 0. That is, there is no covariance. You can't really, if they vary independently of each other, you cannot find a pattern of covariance being either greater than 0 or less than 0. Now, covariance of a random variable with itself, is, so if you remember from our discussion of variance of a random variable, it was expected value of x minus mu x whole square, which also can be written as expected value of x minus mu x multiplied by x minus mu x, and as you can see, it is covariance of x with itself. Okay, that is known as the variance of a variable. Now, let us look at the two variables that we have been talking about. That is, in our particular example, we have been talking about the student test score and the student teacher ratio. Now, we plot the student teacher ratio and the test score, student teacher ratio on the x axis and test score on the y axis. So, for each of these dots on this scatter plot, each of these dots represent a particular district. So, this dot, for instance, represents, say, district A. Suppose this is district a particular district A, then the x coordinate indicates the student teacher ratio for that district A, and the y coordinate indicates the test score for that for all the average test score for all the schools in that district A. Suppose we have another district B over here. So, then again the x coordinate will be related to that district B, and the y coordinate will be related to that district B, and so on and so forth. So, each of these dots gives you information, a two-dimensional information about the individual districts. So, now can you see, when you plot all these points, can you see any kind of pattern in the data? In the sense, can you say typically that as x goes up, does y go up or does y go down? Can you see a positive pattern, that is a line that goes through like this? Can you see a negative pattern, that is a line that goes through like this? Okay. So, maybe you can sort of see a negative pattern in this particular case. So, let us go forth a little more. So, now we come to the idea of the correlation between x and z. As we said before, the covariance of x and z is in the units of x and z. But typically when you are trying to understand, trying to gauge how much two variables are correlated, if you have it in the units of x and z, you cannot really get a understanding of how much they vary with each other. So, what you want to do is you want to make it a unitless quantity. So, you divide it by the root of the variance of x multiplied by the variance of z. So, this is in the units of this is square of the units of x multiplied by the square of the units of z, and the root of that means just the units of x multiplied by the units of z. In the numerator also you have the units of x and units of z. So, you have sigma xz by sigma x sigma z. This is a unitless quantity and it is called Rxz, or the correlation coefficient. Now, correlation coefficient varies between -1 and +1. Okay. So, if x was varying exactly with x, so here also you would have root of variance of x, here also you would have, which is variance of x, here you would have variance of x. So, variance of x divided by variance of x, you would have 1. That is, if it was varying exactly similarly, then you would have 1, and if it was varying exactly opposite to each other, then you would have a correlation of -1. So, correlation of xz equals to 1 means perfect positive linear association, and correlation of xz equals to -1 means perfect negative linear association, and if it is 0, it means no linear association. So, let us look at some of these examples. So, for instance, if you look over here, if you look at the varying pattern over here, it's sort of a line which goes like this. If you look at the varying pattern over here, it's a line which goes like this. I'm sorry, it's not. I'm not able to draw this very carefully. Okay, let us try that again. Okay, that's the best I will be able to do. But anyway, so here you see that there is a positive correlation. As x goes up, y also goes up. Here there is a negative correlation. As x goes up, y goes down. And you can see that it says so over here. Over here you can't really see any kind of pattern. It is sort of all scattered all over. You cannot say whether correlation is positive or negative. In this particular case, for this range of values of x, as x goes up, y goes up, and for this values of x, as x goes up, y goes down. So, on average the correlation is 0, but just because on average the correlation is 0, you can't really say that there is no relationship between x and z. What is happening actually is that there is no linear relationship between x and z, but there is in fact a non-linear relationship between x and z. This is why we said that just in this particular case correlation is 0. Just if the correlation is 0, you cannot say that x and z vary independently of each other. That is not that we had talked about that previously. So it does not say. There may be a non-linear correlation. Now we come to the idea of conditional distributions and conditional means. Okay, so conditional distribution. So the distribution of y given values of some other random variable x. So the distribution of test scores given that STR is less than 20. Okay, so let us go back to our description of the height and weight. So if you remember, we got a hill kind of a shape over here. Now suppose we wanted to see that for all the people who had a height of exactly 5 feet, how does their weight vary? So suppose you actually cut this hill and you take the cross section of the hill and you look at, so basically what we will do is we will remove some of these lines over here, and we will take only the line that is, we will take only this particular, let us take a different color. So we will take only this line and we will cut the hill over here. So you may get a distribution of weight for all the people who have a height of 5 feet. You may get a distribution of weight which is like this. If you cut through, if you think of it as a hill and you cut through it, you will see a cross section which is like this, and the outer perimeter of that cross section will give you the probability density function for all individuals whose height is 5 feet. What is the probability density function of their weight? Okay, so this is basically the idea of conditional probability density function. So conditional distribution says distribution of y given values of some other random variable x. In that particular, we said that we gave a value of 5 feet for the height. What is the distribution of weight given the values of all people who are 5 feet tall? In the case of the test score, suppose we are given that student teacher ratio is less than 20, then what is the distribution for all those schools? See, even for school districts where the student teacher ratio is less than 20, it's not that all of them will have the same achievement scores. There will be variation between that also. So when you look at that distribution of those test scores, that is called the conditional distribution. So now in that conditional distribution, you will also have a conditional expectation and conditional moments. So basically it is the mean of this particular distribution. The mean will be the conditional expectation. The variance of this particular distribution will be the conditional variance, and you will have skewness and you will have kurtosis for this particular distribution. So these are called the conditional moments of that particular distribution. So expected conditional mean will be the mean of the conditional distribution. Expected value of y given x equals to some value x. So this is a very important concept in the case of linear regression, as we will find out later. Conditional variance is variance of the conditional distribution, variance of that distribution given a particular value of some other random variable. That is, expected value of test scores given STR equals less than 20 is the mean of test scores among districts with small class sizes. Now suppose we take the difference in means of two conditional distributions. So we take all the small class size districts and all the large class size districts. We take the conditional means of all the districts with small class sizes, and we take the conditional means of all the districts with large class sizes, and we do subtract this from this. Then we will find the difference in means between the two conditional distributions. Other examples of conditional means might be when you are looking at wages. So suppose you have y is the wages and x is the gender. So you put in the one variable takes values of all the wages that people get, and the other variable takes the values of gender. Now this is of course a discrete variable, okay, but given, you might find that the conditional mean of those who are the males in the group may be higher than the conditional mean of wages, given that an individual is a female. Okay. Mortality rate of those given an experimental treatment. So suppose someone is trying to develop a particular treatment for some kind of cancer, and they may try to look at a test versus control group. So the control group will be the not treated group and the test group will be the treated group, and they may want to find that in which group people are more likely to live or die. Okay, so that would be a mortality rate, and so on and so forth. So if the expected value of x given z is constant, you know, if there is no variation in that, then there is no correlation between x and z. So basically what we are saying is that basically there is no covariance, there is no variance in that distribution. The correlation will be 0. This we will talk about a little bit more later. Okay. So now this part of the presentation, this part of the lecture we will talk about in a different lecture.